Okay, so let's get this kicked off. Our first presentation, we've got Dexter Lewis from the Electric Power Research Institute. He's going to talk about automating overhead power inspections. And Dexter, I'd like to hand it over to you, sir.
Thank you, Gavin. Hi, everyone. So just a quick overview. If you haven't heard of the Electric Power Research Institute, we're a nonprofit research organization primarily focused for electric utilities. Um, I've been with EPRI, I guess, about 6 years. Before that, was in the electric utility industry and research for about 10 years, um, running R&D projects. So the work that I lead at EPRI is primarily related to unmanned aircraft applications and uses. And because these technologies are advancing fairly quick, it's shifted a lot of my research into trying to automate the entire inspection process. The motivation for doing that, it fundamentally comes down to some previous work that we had done, where we see that manual drone flight operations doing comprehensive transmission inspections can be slow and time consuming. Primarily, it's a function of how long it takes you to get from structure to structure in these right of ways that don't always have parallel roads or easy access in and out. A study that we had done shows that drone automation can improve your inspection speed. Primarily, the motivation is that it allows you to stand in one location and safely operate an aircraft, a couple of thousand feet away from you to the extent of your line of sight, and do so in such a manner that it can safely maneuver around a complex transmission or distribution structure, capturing the imagery you need to perform that work. And as such, again, that just eliminates that need to go to every single structure, which can reduce the time it takes to perform this work and ultimately reduce the cost to perform it as well. Now, you may argue that for some inspection processes, you do need to go to every structure, especially if you're doing like a ground line survey or something like that. And what I would say is that automation still can help in these environments, even when you're standing at the base of the structure, because there are some environments in our utility world that are pretty noisy. This is an example at a training environment where we were doing some automated flights with the Skydio S2 aircraft. And you can see there's some overhanging vegetation that are real obstructions. And if you were standing at the base of that tower, even though you're there, it's still difficult for you to maintain your situational awareness of where you are with that aircraft relative to the vegetation behind you or the conductors in front of you. So I'll say that a lot of our research has shown that automation is feasible, but depending on the inspection that you're trying to do, it can be difficult to get it right. And what I mean by that is getting the right imagery or video at the right perspective and at the right spatial resolution in order to complete that inspection process and reduce the likelihood of having like a false negative of missing something that's there. So examples on the left are a few of the images and perspectives that we get from our traditional methods of a person flying in a helicopter, hovering near the line, using a camera to really focus in and get a high resolution photo. Versus on the right, this was our first attempt at automation using LiDAR models of our transmission structures to build flight plans that would have a waypoint-based navigation of an aircraft moving and capturing images of a transmission structure. You can see the difference there. So that really only becomes a challenge if you're wanting to see that type of inspection detail and you get back to the office and you realize that you don't have it. Now you got to go back into the field. That costs money and takes time. So the way that utilities kind of reduce the risk of missing something important today is that they develop these shot sheets that they give to their drone operators. They kind of give an idea of where the areas of interest are and some detail related to how to capture those imagery to perform that comprehensive inspection. Now, those are great, but in reality, those don't really help in the automation use case because you can't translate those shot sheets directly to a human. So the question that we had in this research project was, how do we basically teach drones to operate around these complicated structures, getting imagery of sufficient quality to perform this inspection? We built a workflow and tested the workflow. You could argue whether or not it applies. It was kind of in the best case scenario. So we went to a training environment, captured a very high resolution LiDAR model, about 400 points per square meter, tied it down with survey points, and and then used that information to build a local coordinate system to a structure in that site, and then used that coordinate system and those axes that we defined to define our image capture specifications. We did it objectively, so it said, we want an area of interest at this ground sampling distance or at this spatial resolution, and then we provided this information out to technology providers and drone service companies to come and test their automated solutions. With the information that we provided, they were able to back calculate using their camera parameters where to actually put that aircraft to capture that image how we defined. So again, we tested this in a training environment earlier this year, had an array of different solutions. A few of them used the LiDAR data that we provided. Other ones said, we don't need it. We have kind of a roaming approach, and I'll talk about that in a second. We tried all different kinds of technology, some small payloads, some 100 megapixel kind of image capture payloads that says, well, can we just stay at a further distance and get a wider field of view and get the imagery that you need. So in summary, I'll just kind of summarize the results of there. Is that we really saw two approaches. The first one being trying to get a minimal yet optimal workflow of getting the perfect picture, but that has some challenges. I've listed them there, but primarily it comes down to being able to put your aircraft and point your payload at an object in space based off of a LiDAR model. When you execute that, you're going to have challenges from just your repeatability to repeat that due to GPS error and the accuracy of your LiDAR data and any error between your aircraft payload and its sensor systems. So again, we did this in a scenario that was kind of best case. We gave a very high detailed LiDAR model and had, again, survey points out there, and companies brought out RTK systems that would sit on top of those survey points. We don't have that in the real transmission right of way, but it's just, we tried to just see in the best case scenario, how well could we get it? But at the end of the day, we still struggled with some of these challenges. A lot of them due to framing, perspective. And then even when you get those two things right, you do have the challenges of, is the object of interest in focus, and is the lighting sufficient to do the inspection? Another approach is this kind of blanket approach. This was imagery from a Skydio aircraft. What you do is you kind of define a volume around a structure. You define your capture parameters, which axes you want to rotate around, what your side lap and overlap is, and your spatial resolution. This worked well, but in reality, again, it's got its own challenges from the number of data that you get, and that's important when you think about operationally deploying this for, structure after structure after structure. What I'm showing you here is the summary of 240 photos that were captured in about 14 minutes, but moving that data from the field to the office is always going to be, or is a challenge today. And then working with it in some type of usable fashion, to complete this inspection. It's difficult to recall the imagery exactly, based off of a, let me think. There needs to be some improvements in the workflow related to reviewing this imagery. You could think about leveraging like a geospatial GIS layer. But if you plop 240 photos all around a structure within a fairly small area, even that can be somewhat difficult to use just if it's two-dimensional information. There's a three-dimensional component to this data, so I'd like to see some more development in this space of how can you interact with this imagery in a way that almost feels kind of like you're manipulating a 3D model. And I don't mean creating a structure from motion or photogrammetric model, because I see that in the past you lose some of your spatial resolution detail when that model is created. So I'd like to see something related to how can you interact with this imagery based on kind of an oriented image viewer. There's a couple other things there. So the collection time, whenever you're collecting this much data, and then trying to optimize on these different parameters that you have of manipulating how this aircraft rotates around the structure. Here's an example of how those parameters can be changed, and it's, in my experience, it's just really difficult to get a inspector to give you the Goldilocks answer of, you know, what's the optimized setting. If you showed them these images, what I'm showing you here is 3 rows of images from an autonomous flight with 3 different standoff distances to the object. So the top row being 5 foot, the middle one being 10 foot, and the bottom being 15. And if you zoom into those images at full resolution, you can kind of see the layer of detail there. And if you asked an inspector which one do you want, you could probably guess which one they would say. The top one, because you can see higher spatial resolution, even the strands of the conductor. But if you think about how you collect this data, it also has a trade-off with how long it's taking to collect it, as well as the number of images that you got. So optimizing for that quantity versus quality can be challenging. One thing that I'm seeing with these blanket image capture approach, I guess I went on a tangent on this on the previous video, but I'd like to see some advanced workflows in terms of interacting with this data. Some type of oriented image viewer or pose estimation. If I know that I have sufficient blanket coverage from all these different angles and perspectives, what's the best way for an inspector to interact with that information in an efficient workflow that allows him or her to kind of keep their situational awareness of where they are in that image as they move to the next image, or where they are in that structure. One kind of thing that I hear a lot when you think about collecting all of this imagery and how we're going to deal with it is that AI will help in this space. And I think I'll agree with that, but I would just say that in today's environment, some of these models need improvement. And what I see in the private industry and even utility internal efforts is that there's a lot of work being done and people are solving pieces of the problem. But in reality, when you think about the visual inspection task of overhead transmission or distribution, the list of objects of interest and the list of their failure modes, and then just the different types or construction types of some of these really makes that prediction inspection task very difficult. It's a very complex problem. So what I'm trying to share here in this table is that there are some models out there. When you look at, again, what's being marketed, people have a piece of the problem, but when you really get into what are the inspection requirements and do you have a model to handle all of those inspection requirements, to my knowledge, that does not exist. Now, there is some opportunity in the short term for AI to support this image review process, especially with this first kind of check of, is the image of sufficient quality to be reviewed, for an inspector. That's things like, and that's pretty simple stuff. Is it overexposed, underexposed? Is the object of interest in focus? Then you can kind of stage some of these AI algorithms, I suppose, or machine learning algorithms, to help with other things like, can you show me all the images that align to a certain perspective? So this kind of image similarity task. A little bit further down the maturity curve, but certainly of significant impact to the workflow, is object detection. Can you tell me what's in this picture? Can you tell me where the arrestor is, where the conductor is, where the pole is, etc.? And then if you can identify those objects, can you discern the difference between when those objects are healthy versus defective? So again, I think we're all kind of working towards that object detection and defect recognition use case, but recognize just the complexity of the challenge, not only the number of objects of interest, the perspectives and how those images were captured, and then just the lighting challenges that you get from real world data collection. So in my experience, I think that There's a lot of potential from academia, private industry, utility efforts to advance this space, but there's just a lack of data that's available in industry to accelerate the innovation here. So real quick, I'll say that EPRI is trying to solve that. It's not an easy problem to solve by any means. There are, legal challenges or concerns or risks, I guess, when you think about collecting imagery and then sharing it and then releasing it publicly. You can think about Google Street View and some of the things they must do before they release their data, removing personally identifiable information and such. But long story short, we've gone through that effort on some data sets, and we're happy to share them to support some of this work. If you're interested in any of these, I'll put this link in chat. We're sharing these data under Creative Commons licensing, and it may have a share-alike term depending on if those images are labeled or not. Real quick, a couple of these examples of what these data are. Here's an example of some insulator data that we've labeled. It's called our ID. It's bounding boxes of the actual insulator string and then individual bounding boxes on the insulator shells and a condition rating if they're healthy or broken or flashed. We have some segmentation data that we created synthetically through computer-generated graphics. We have that to share as well. We have some unlabeled imagery of just generic transmission defects. We're sharing these under Creative Commons share-alike terms that basically says if you take these data and build upon them with any derivatives, we're asking that you contribute those contributions back to the data set. An effort to get industry working more collaboratively in this space, sharing some of the labeling work that everybody's doing, trying to solve the same thing. Did the same thing with overhead distribution imagery. We've got about 30,000 images we've released in this space. And coming soon, a couple of teases. We did a demonstration project with a ground-based imaging camera system, just looking up at poles as you're driving by. We have that to share. And then some of the geospatial data that I was talking about that we collected in that automated inspection task back in August. We have that to share as well. Our motivation for sharing this, to be honest, is to, again, drive innovation. And the approach that we're trying to do with that is kind of documented here in this workflow, where we get data either from utilities or from ourselves. We'll do a little bit of review and cleaning, try to share that out to model developers, whoever wants it. And then we'll run these data science competitions trying to demystify some of these data science, image prediction metrics. That's one thing. If you start to follow this space in the private industry, you hear all these accuracy numbers and precision numbers and mean average precision, intersection over union. It's math at the end of the day, but it can be difficult to interpret in terms of, well, what does that mean for a critical infrastructure use case? What's my tolerance for one false negative? It can be a little difficult to interpret. All that being said, we tried this and it worked. We created a competition on IEEE Dataport. It was a pretty easy thing to do. It was no cost to do it, and we didn't give any financial incentive. A lot of times with these data science competitions, you put a prize out there. In this case, we were just kind of experimenting. We didn't do that, but we still did get some submissions on our ID dataset competition. And here are some of the example intersection over union mean average precision numbers of how well that model worked. So expect more of that from EPRI in the future. A lot of this work, here's where my shameless plugs comes in. A lot of this work is coming back to a project that I manage, this advanced distribution inspection project, where we're trying to use automation for data collection and then data interpretation. If any of this is of interest to you, there's my contact information, reach out. Within this work, we kind of have these 6 tasks. Again, you can classify the first 2 of, how do we collect the right data autonomously? So building specifications, and then how do those specifications work in a real world distribution environment? And then the tasks 3 through 6 are all around how do we build labeling guidance when we are embedding information in these images to train AI models. What's our taxonomy of terms? So what's all the standard nomenclature we're going to use to describe these objects? what's the impact of synthetic data, and then lastly, hosting these data science competitions. And the results out of this are very in line with those tasks. I'll just leave them there for you to kind of read through. But at the end of the day, what we're trying to do is provide utilities an understanding of where the state of the industry is, where some of the industry gaps are, and trying to address those in a collaborative fashion to improve this use case of automated inspections so that utilities have it as an option to deploy when they decide they want to inspect overhead transmission and distribution infrastructure. So that's all I had. Thank you.
Thank you, Dexter. Got some questions came in. Yeah, big thumbs up. Several people said, nice job. So great. So Dexter, have you experimented with the oriented imagery catalog from Esri?
I have not experimented with it. I have taken some of the data that we've collected from that test, and I am working with Esri and hoping they will build it for me and experiment with it. I've seen some capabilities with it, but I don't know if it will. I don't know if it will work for that use case as I'm kind of describing, but I hopefully will know soon.
Okay.
So yeah.
Yeah. There's a request for you to post your contact info again.
Okay.
Or if Ann, if you have that, put that in the chat box, please. Okay, questions about the drone operations. Is some of the challenges around the beyond visual line of sight rules? How's that been going with, your scenario to sit in one spot and fly a long corridor beyond the visual line of sight? Where has that been going?
Yeah, so that's a area that I try not to spend my time working in. There's a lot of regulatory requirements. What I try to do is think about a future state of when we will be flying beyond visual line of sight as a part of everyday operation. And when that state comes, how will we be operating our aircraft? And to me, it makes sense that they'll be autonomous, or as autonomous as they can be. Just because if you're standing in one location and trying to fly a mile away and you can't see your aircraft, you don't have any situational awareness of how close it is to the structure or the object behind you. So all the work I've done and showing is within line of sight, but it's basically stretching the legs of what you can do within line of sight. And in all honesty, a lot of the aircraft that we're flying are hovering type aircraft with lower flight times, so 30 minutes per se. And you also have wireless link, transmission limitations in some scenarios. So even if beyond visual line of sight changed today, for some of this comprehensive inspection work, you may still have people out in the field changing batteries and maintaining wireless link and all that stuff.
Okay. Yeah, I'd seen an outfit in Austria that was working with a gas-powered rotary engine. Well, the rotary engine means less vibration, but that thing runs like 6 hours at a time. So they are banking on beyond visual line of sight. Other questions about the drone operations, just some of the challenges that different jurisdictions or areas have different privacy rules.
So I don't know that I've quite ran into a lot of it with the work that we do. There have certainly been work operations in the distribution environment with some of our case studies where when you get into those urban settings and you're flying a drone overhead, you can hit some customer complaints. Usually you can address those if you tell them who you are and what you're doing as a utility. But I think some of this privacy concern, whether it's legitimate or not, is restricting some of this collaboration between utilities. We have collected data from this distribution circuit and another utility has done the same. But what we're trying to do with all the data that we share, we go through a anonymization process. So I look in the background and see if I see any faces or license plates, and we scrub it out. And then we also remove a lot of the metadata that's in the image as well. So the GPS information and the timestamp. And we'll either completely strip that off the images. So those data that I showed to you, a lot of that's gone, or we'll translate it into some other spot in the world that is in the middle of the ocean. At the end of the day, it's the individual utilities call on whether they're willing to contribute. And I would argue there's probably some data that you don't want to or can't, but there's probably a lot of it that you can, if you can do it intelligently and protect it. So.
Okay. Yeah, I remember some discussions a year ago at, I can't remember the event, about that the hope was to get municipal, state, and federal to not provide an exception per se for the utilities, but allow a mechanism where the privacy concerns would not be, that data could be certified to be sort of locked out of, public view. So questions about your first scenario about flying in close around the utility lines. The situational awareness, are you aware of how things are going with the application of like the drone-based radar, LiDAR, ultrasonic for situational awareness for the automation of that drone operation?
Yeah. So it's one navigation technique, right? You see it in the self-driving car industry. You got vision-based systems versus LiDAR systems. I think I haven't done a lot with LiDAR as a navigation approach on an aircraft. Again, a lot of the work I showed was from the vision-based sensors on the Skydio aircraft, but those have limitations in some environments, low light, for example. So if you could get the payload cost low enough, I think the ultimate solution would be some type of combination of LiDAR and vision-based collision avoidance systems, as well as onboard, navigation decision making. Hey, can I follow the conductors based off of my visual understanding of where they are, or the LiDAR model that's picking them up and using them as a navigation technique or a collision avoidance technique? I think either would work. I just think if you look at the price differences, at least today, you may know more than me, it's probably cheaper to have a vision-based system than a LiDAR-based system.
Yeah, from what I'm hearing, the vision-based systems at the most, for cost effective, although there's some experimentation with certain low-cost flash LiDARs. I'd also seen where, ultra-wideband beacons being used in the rail infrastructure. Proposals for other placements are transmission towers, distribution poles, that sort of thing, because those range very well. But again, like you said, you need a pretty detailed model of that whole structure, the cross arms and everything, and it has to be kept up to date. So you think maybe it's going to take a combination of both, is an ongoing program of your blanket imagery / or LiDAR, and then the close-in topical inspection flights?
I think you want to use what data you've got. So, if you have LiDAR from post or vegetation management surveys, on certain transmission levels, use that to your advantage. I guess you play, forecaster here and try to think where this technology is going to go, which can be difficult. But with all this AI data sharing that we're doing, a lot of it is to facilitate this post capture inspection process. But I don't think it's that far of a stretch to consider all the work that may be done in that post process and begin to put it on the aircraft itself, or on some, local computing machine that's talking to the drone while they're out there in the field. If that's the case, I'd like to see something that's not limited by having accurate LiDAR models, because when the tree grows in the distribution environment, your model's different. So I want to see the technology evolve to where you've got onboard decision making, and whether that's a vision sensor feeding it or a LiDAR sensor feeding it, I think both could be great. But almost like following the conductor until it gets to a structure, and then having enough understanding of, well, here's that structure construction type. Here's where those components of interest are, and then using a closed loop kind of real-time sensor-based decision-making scheme to capture those images that give you the best comprehensive inspection.
Yeah, I'd agree, and I think there's the benefit of this, this huge concentration of R&D on the autonomy for vehicles, but also closer related, all that research. I'm amazed what I'm seeing out of Japan and Eastern Europe, and the R&D for real-time situational awareness for proposed delivery drones and drone taxis. So this spillover, I think, is going to help out in the long run. The data analytics side, this idea of you've got this library of different, like insulators in different conditions, different features in different conditions. Somebody had asked about, what about the examples in different weather environments? I don't know how much that would affect the differences in what those are seeing.
Well, I've looked at some images and seen snow on top of insulators, and that changes the physical shape of them, which I imagine could trip up an AI algorithm. So we're not prejudiced to any kind of the environment. It's mainly a function of which data do we get from either utilities contributing or research projects going out and collecting. I think I can't speak intelligently about the impact of the weather conditions, but I do think lighting and perspective could certainly give you a few challenges, and those again could be related to weather conditions.
I see. So lighting, yeah, so perhaps different examples in different lighting environments. So we're wrapped up now. Dexter, thank you very much. Very insightful. Learned a lot about this. We're going to move on to our next session.